So let's recall the argument principle. The argument principle applies when we have an analytic function on a domain, and in this domain there's a typical curve gamma, and it's inside omega. And the inside of gamma, omega, is contained in the domain of f except for finitely many poles, w1 through wl, which are in omega. And we're also assuming that f is non-zero on gamma, and that but f might be zero at some finitely many points inside of gamma in omega. And then we're going to denote the orders of these zeros and poles by n sub j and m sub j. So n sub j, I'm introducing new notation here, which is going to be convenient for us. So the order of a zero of f is going to be, so we have O for order, subscript z for 0, superscript f for the function. So the order of the 0 of f at zj. So that's how you would read that. And then we have mj, the same thing but for poles. So the order of the pole for f at wj. Then with these notations, the sum of the orders of the zeros minus the sum of the orders of the poles, that is 1 over 2 pi I times the total change in the argument as z traverses the curve f composed with gamma. So you have this closed curve gamma, then f composed with gamma is a closed curve which is going to potentially wind around the origin, and the total change in the argument as you wind around divided by 1 over 2 pi, that's also the same thing as just the total number of times that composition curve winds around 0. So that's what this left-hand side is counting. So you can count the number of times f makes this curve gamma wind around the origin. You can count that by just counting the multiplicity of the zeros and poles appropriately. So that's the argument principle. So what the argument principle is really good for is finding qualitative information about solutions to equations. So essentially just counting the number of solutions to equations involving analytic functions. So for example, if you take a real number lambda greater than 1, we can look for solutions to z plus e to the minus z equals lambda in the right half plane. So we can deduce the existence of solutions to this equation because that's going to be a 0 of z plus e to the minus z minus lambda by looking at how that function maps a curve and how many times that mapping of that curve, of that closed curve, goes around the origin. So what we want to do is just look at a suitable closed curve and try to deduce how many times our function sends that around the origin. So the curve is pictured there. When r is very large, it's going to enclose a very large portion of the right half plane. So that seems to be a good curve to work with. And we'll just consider the function f of z equals z plus e to the minus z minus lambda. So we're looking for zeros of this function. And so what we can do is look on the interval of I times negative r to r on the imaginary axis. And so on that curve, we just have I times y. And so we have iy plus e to the minus iy minus lambda. And just by definition, this is, let's see here, it's a cosine of y minus lambda. That's the real part. And then plus I times y minus sine of y. Right, because we have just apply the definition of the exponential and use that sine is odd. That's how we get the minus sine of y. Minus sine of y is the same as sine of minus y. So the key thing to notice now is that because lambda is greater than 1, when you subtract that off from a cosine, this is always going to be less than 0. So the image of this vertical segment here is always going to be strictly in the left half plane. Right, so basically the image here, when you apply this f, that's always going to be in the left half plane. And let's see, so we can put our lambda, so negative lambda is less than -1. So if this is -1 here, our negative lambda is going to be here. So this is negative lambda. And the x component of this image curve is just going to vacillate around lambda, right? You're just going to have this, a negative lambda. You're just going to have this addition of cosine of y. And the second component here, y minus sine of y, that's just a little bit of a perturbation on y. So as y goes from r to negative r down that segment, this is going to go from just roughly I times r to negative I times r, with just some minor perturbations coming from sine of y. So sine of y sometimes is going to be moving with the y and sometimes against it. So basically, I mean, you're going to have something that looks like, so if this is, so you're going to have something that looks like, I don't know, roughly like this. So that's going to be the image of this segment along the imaginary axis. It's going to be some kind of thing like this. Okay, and then the part that's, so you have the r e to the I t part as well. That's that right half circle there, and t is between -pi/2 and pi/2. And now that, when we plug that in, we have r e to the I t, and then we have e to the minus r e to the I t minus lambda. And that is r e to the I t plus e to the minus r cosine of t times e to the minus r I sine of t minus lambda. And the thing to notice about this is that the magnitude of this term here, so the norm of that is the same as e to the minus r cosine of t. But between -pi/2 and pi/2, cosine is non-negative. So this is an exponential of negative or 0 values, so that's going to be less than or equal to 1. And so that thing has magnitude less than or equal to 1. And so this 1 minus lambda here, the absolute value of that can't be any worse than lambda plus 1, say. But what we can do is when we can assume that r is really large here. So assume that r is large enough that the norm of r e to the I t is bigger than the norm of that other stuff, e to the minus r e to the I t minus lambda. So given that, if we look at r e to the I t in the image picture, so we have like r e to the I t, right, that's this term here. This other term, since the length of that is less than the length of r e to the I t, that's never going to hit 0, right? So blue and green have to add up to be red, the actual curve. So So the blue and the green have to connect up here. So the blue plus the green, I mean, you can have the green curve like coming out like this, but it never is going to touch the origin. All right, so maybe it's something like that. So blue plus green is red. So maybe our actual curve looks like this. But the point is that it's never going to hit the origin, right? So it's just going to be a relatively small, relatively speaking, a small perturbation just from that r e to the it curve. So we have to, this red curve, the image curve, if we follow it starting at e to ir, follow it down and then around, that's going to go down this squiggly thing starting in the second quadrant, working its way into the third, and then the r e to the it plus that other stuff has got to take us from the third into the second, because r e to the it goes into the fourth quadrant, and then the first, and that green is relatively small, so that's only going to be a small perturbation from that fourth quadrant to first quadrant movement. So ultimately, we then have to move from the third to the fourth quadrant, and then into the first, and then back into the second. So that's going to give us one circuit around the origin in total. And so that means that by the argument principle, the number of solutions in the right half plane has to be exactly equal to 1. And so the argument principle that tells us that 1 has to be equal to the sum of the orders of the zeros of our function, because our function doesn't have any poles, of course. But then that means that there must be just a single zero of order 1. So this implies a single zero of order 1. And so this argument applied for any r sufficiently large. So as long as r is sufficiently large, then all we're going to see is that there's a single zero of order 1. Right? Making r any bigger doesn't find us any more zeros. So there must be a single zero of order 1 in the right half plane. Our next theorem is a formalization of the kind of argument that we gave in the last two examples. So basically in the last two examples, we had something like we had a curve that was winding around the origin. So let's see, here's our plane. We had a curve that was winding around the origin like this some number of times. And then we had a curve that was staying somewhat close by to that curve. So the picture looks like this. We have the red curve winding around, and then the blue curve is some distance away from that red curve. So for each parameter value on the red curve, the corresponding parameter value on the blue curve is separated from it by this black arrow. And the conclusion here is that if the black arrow is sufficiently short, so if the black arrow is less than the distance from the red curve to the origin, then we can be confident that the blue curve winds around the origin the same number of times as the red curve. So if we have a short black arrow is going to, of course, imply that the red curve and blue curve wind around the origin, wind around 0, same number of times. At the end of the last video, I think I gave an analogy using the sun and the earth and the moon, but maybe a better one is that of a man walking a dog on a leash around a tree. So if the man is the red curve, walking around the tree some number of times, the tree is the origin, and he has a leash such that the length of the leash is shorter than the distance from him to the tree, then no matter what the dog is doing, which might be, kind of moving around all crazy and looping around the man and such, well, because the leash is short, even though the dog might be doing some crazy stuff relative to the man, relative to the tree, the dog is still making the same number of loops around the tree that the man does. So that's the basic geometric intuition here. And so this the red curve. So the way we're going to apply this is that the red curve is going to be some analytic function f applied to a typical curve gamma in the domain of f, and the blue curve is going to be g composed with gamma. And so basically what we're going to find is that applying the argument principle here, that the number of times if we know along this curve that let's say that f g minus f, the distance between g and f on the curve gamma is less than the length of f on the curve, so on gamma, then the number of times they wind around should be the same by this geometric picture, and then by the argument principle, that's going to imply that they have the same number of zeros. So f and g have the same number of zeros inside gamma, right? Because the number of zeros inside gamma is the number of times that g and f composed with gamma wind around the origin, but they're winding around the same number of times by this geometric picture. So the formal statement of that intuition is encapsulated in Rouche's theorem. And so Rouche's theorem says that if you have two analytic functions on a domain which contain a typical curve and it's inside omega, then if the distance between f of z and g of z along the curve gamma is less than the distance from f of z to the origin along gamma, then f and g have the same number of zeros in omega up to multiplicity. So that is counting the order. So for the proof of this, we want to try to apply the argument principle. And so in order to apply the argument principle, we want to know that our functions are not zero on the curve gamma. So first note that f and g are not equal to 0 on gamma. So the first one is that if f was equal to 0, so f can't be equal to 0 on gamma because since you have this is greater than or equal to 0, right? You see that f is strictly greater than 0 along gamma just by the assumption. Okay, so that's for f. And then for g, if g were equal to 0 on gamma, then plugging that into this inequality here would say that f at that z is strictly less than f at that z, and that doesn't make any sense. Okay, so both of our functions are not 0 on gamma. And now what you want to do is consider then that, so what we're going to do is take this inequality and divide by f of z. So the inequality given is equivalent to the norm of 1 minus g over f of z is less than 1. Okay, so i.e. norm of 1 of h of z minus 1 is less than 1, where h equals g over f. And that inequality holds, so this is for all z on the curve gamma. Okay, so thus thus H composed with gamma. So you got to think about what this inequality means. It means that H of gamma doesn't get more than a distance of 1 away from the point 1 in the complex plane. Right, so it's contained in a disk of radius 1 around the point 1. In particular, it's contained in the right half plane. So thus H composed with gamma is contained in the right half plane. And so the change in arg that H composed with gamma makes as you go around gamma is 0, right? So it doesn't go around the origin at all because it stays in the right half plane. So the number of times H composed with gamma encircles the point 0 is 0. So from the argument principle, so the argument principle implies that the sum of the orders of the zeros of H, so that's the sum, so Zj is a 0, Zj a 0 of H is equal to the sum of the orders of the poles of H. So this is over points Wj, which are poles, so Wj pole of H. The basic point now is that if you look at H, so the definition of H is that it's G over F, right? So on the right-hand side, you have zeros of H here. So roughly these zeros of H, they should correspond to just zeros of G, right? And so basically this looks like is that the sum of the orders of the zeros of G. And so basically you want to say something like this is the sum of the orders of the zeros of G at these points Zj. And on the right-hand side, when do you have a pole of this function h? Well, you have f in the denominator here, so you're going to have a pole when f is equal to 0, right? So this should be the sum of the orders of, so the order of this pole for h should be the order of that 0 for f at those points wj. And so you should get the sum of the orders of the zeros of G is equal to the sum of the orders of the zeros of F. The only problem is that you have to be just a little bit more careful than this. So basically this type of argument only works when F and G are not simultaneously 0. Right? Because if you have H is a, you have G is 0 and F is 0 at the same time, you get 0 over 0, and that could be a pole or a 0. And things become a little bit more complicated, so you have to just analyze those situations. So let's see what we can say here. So it helps to just look at the possibilities for the function h at various types of point z naught. So possibilities for h at a point z naught. So the first possibility is that f of z naught and g of z naught are both not equal to 0. Then in this case, z naught is clearly not a 0 or a pole of h. So z naught is not a 0 or pole of h. Okay, so 2, is that one or the other of the, well, 2 and 3 are going to be that one or the other of them are. So let's say that f of z naught equals 0, g of z naught is not equal to 0. And so if that is the case, then since f is our denominator, this must be a pole of our function h. So let's see, so we can write h of z. So if we look at locally around z naught, our function g is not equal to 0, so we have b naught plus b1 times z minus z naught plus dot 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 over our f is 0, so that's going to have a 0 of a certain order, say n, so it's going to be an times z minus z naught to the n plus dot dot dot, where that an is not 0, and this equals 1 over z minus z naught to the n times b naught plus dot 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 over an plus dot dot dot, and this thing here is not equal to 0 at z naught. So we have an analytic function there which is not equal to 0 at z naught, and so we see that we have a pole of order n at z naught for h. So what we find is that the order of the 0 of f at z naught in this case is equal to the order of the pole. So h has a pole then at z naught of that order. The third possibility is the other way around, so f at z naught is not equal to 0 and g at z naught is equal to 0. And then in that case, it's just sort of flipped around. So you have a 0 of some order, let's say m, so you have bm z minus z naught to the m plus dot dot dot. F isn't equal to 0, so that's a naught plus a1 z minus z naught plus dot dot dot, and that's equal to z minus z naught to the m times bm plus dot 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 over a naught plus dot dot dot. And this same thing, that function's not equal to 0 in brackets there at z naught applies. So what we see is that h has a 0 of order m at z naught, which is the same as the order of the 0 of g. So in this case, we find that the order of the 0 of g at z naught is equal to the order of the 0 of h at z naught. Okay, so basically in this case, h has a 0 at z naught, and up here we had h has a pole at z naught. Okay, and then the fourth case here is that f of z naught and g of z naught are both equal to 0. And this really has 3 subcases to it. So the first subcase, so it depends on the orders of these zeros. So in this case, so the first one is that the order of the 0 for f at z naught is greater than the order for the 0 of g at z naught. So again here, so we have h of z. So this time our g's order, so you have bm z minus z naught to the m plus dot dot dot. F's order, the 0 at z naught for f has order n, and our n is greater than m. So that means that we can, let's see, if we pull out, right, so we're going to pull out the z minus z naught to the n on the bottom there, and the z minus z naught to the m on the top. And then we have bm plus dot 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 over an plus dot dot dot. Again, in parentheses, a function that doesn't vanish at z naught. And then what we have here is 1 over z minus z naught to the n minus m, right, times this function which doesn't vanish at z0. So what we find in this case is that H has a pole, and the order of that pole of H at z0 is equal to n minus m, which is the order of the 0 for f at z0 minus the order for the 0 at of g at z0. Okay, so similarly, so for the second subcase is that the order of the 0 for g at z0 is bigger than the order for the 0 of f at z0. And a similar calculation, so the calculation is similar, H has a 0 in this case. So a similar calculation. So now so if you look at the calculation up here, now m is bigger than n. So when you do z minus z0 over m to the m over z minus z0 to the n, your m minus n is the integer now. So that's going to give you a 0. Has a 0, and the order for that 0 of h at z0 is equal to m minus n, and that's the order of the 0 for g at z0 minus the order of the 0 for f at z0. The final thing that can happen is that the order for the 0 of f at z0 is equal to the order for the 0 of g at z0. And let's say that order is m, say. Then the same type of calculation we've done just shows that h of z is going to be b sub m plus dot 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 over a sub m plus dot dot dot. Right, so they're both going to start their series, power series expansions at the mth power of z minus z naught, and so you can pull that out of numerator and denominator and just cancel. And so again, you can look at this box up here, m and n would be equal, and then those would cancel out. And so in this case, we see that, in fact, h doesn't have a 0 or a pole at z naught. So z naught is not a 0 or a pole of h. It's in fact a removable singularity. So it's a removable singularity. And you can see explicitly h at z naught is equal to b sub m over a sub m. So now if we go back, that's all the possibilities for h. And then let's go back to this here. So we have the zeros of h, the orders of the zeros of h, the sum is equal to the sum of the orders of the poles of h. Right, so we have the sum of the orders of the zeros of h is equal to the sum of the orders of the poles of h. Well, so the sum of orders of zeros of h, so when do we have a 0 of h? So we have a 0 of h. So h has a 0 here, so that's in 4b. H has a 0 so here, so that's in case 3, and those are it, right? So this is the sum over case 3 zeros, right? So this is case 3, the order of the zeros of h that come from case 3, and then from 4b, the orders of the zeros of h. And then that's equal to the orders of the poles. And the poles, the only time you have a pole is here, that's 4a, and 2, right? H has a pole. So this is equal to the sum over case 2 zeros, or poles. So order of a pole from case 2, and then from 4a, the order of the pole wj. Okay, so what do these look like? So in case 3, the order of the 0 of h was the order of the 0 of g. Right? So this is the sum of the order of the 0 of g, right at that point there. And what characterized case 3, that we were not a 0 of f. So zj, so f of zj is not equal to 0. Right, so it's implicit that zj is 0 at g, but the main thing is that we're summing over those zeros of g, which are not also zeros of f. And then in 4b, our h, the order of our 0, is the difference of the orders of the zeros, the 0 for g and the order of the 0 for g and the order of the 0 for f. So this is the sum of the order, so order 0 g at that zj minus the order of the 0 for f at zj. And in this case, so what 4b was is they were, right, so they're both 0, and the order of g, the g0 was greater than the order of the f0, right? So the order, so in this case, the order of the g0 was greater than the order of the f0. Okay. And then I'll write down similar things for the other side. Okay, so there it is. I've written it down, and we have this equality here. And basically, now what happens is that if you just rearrange things here, so you have the order of g zeros here and here. You have minus order of g zeros over here, so you're gonna put that on the other side of the equation. And then you also have order of f zeros here, and then you have a minus order of f zeros there, so you're going to put that on the other side of the equation. And so those orders of, so look at the orders of the order of zeros of g terms. So we have a sum over the orders of the zeros of g where f is not equal to 0, and then we have the zeros of g where the order of that 0 of g is strictly greater than and strictly less than the order of f. And then for the orders, for the zeros of f, we have the zeros of f where g is not 0, and then the zeros of f where the order of f is not equal to the order of g. So basically we're summing over, so our sum for the green terms is over all of the zeros of g where the order of that 0 is not equal to the order of the 0 for f. And for the yellow terms, it's over all of the zeros of f where, again, the order of the 0 of f is not equal to the order of the 0 of g. So I wrote that down here. So we have the sum of the orders of zeros for f, as long as you're summing over the zeros where the order of the 0 for f doesn't match the order of the 0 for g, that's equal to the sum of the orders of the zeros for over the zeros for g, such that the order of that 0 for g doesn't match the order of the 0 for f. So now if you take a look, the only zeros of f that are missing on the left-hand side are the ones that are also zeros of g of the same order, right? And the only zeros of g on the right-hand side that are missing are the zeros of g that are also zeros of f of the same order, right? But those are the same zeros. So the zeros that are missing on the left are the ones that are missing on the right. And their orders of those zeros for f, they're the same by definition as the orders for g, right? So you're adding in these extra terms for zeros on the left-hand side whose orders are exactly equal to the orders and zeros that you need on the right-hand side. And so this is just going to imply that the sum of the orders of the zeros of f of zj, so this is the sum over all zeros of f, is equal to the sum of the orders of the zeros of g. And so this is over all points where g is equal to 0, all the zeros of g. And that was the theorem that we're trying to prove. All right, so I've written in a little summary of the last step of the argument in case that was confusing. So on the left-hand side, the zeros that we're missing, that we're missing counting, are the zeros of f, which are also zeros of g with the same order. And what we're missing on the right is zeros of g, which are also zeros of f of the same order. Right? But these are both just descriptions of the same thing. So what we're missing on the left-hand side are terms for certain zeros, but those are also the same zeros that we're missing terms for on the right-hand side. And furthermore, those orders on both hand sides for those zeros are the same. So we just throw in those zeros with their associated orders, and we're just adding the same terms to both sides of the equation. So we don't ruin the equation, and so we just see that the sum of the orders of the zeros for f is equal to the sum of the orders for the zeros of g. Okay, and that is that's going to complete the proof of Rouche's theorem. So the basic idea is simple to apply the argument principle to this function h, and then roughly speaking, zeros of h should correspond to zeros of g, and poles of h should correspond to zeros of f. But there are some just slight annoyances that you have to deal with, especially when f and g are 0 at the same point. And we just resolve that by looking at the power series and seeing how the orders of the zeros of f and g conspire to tell you what the orders of the zeros and poles of h are. Okay, so again, it just comes down to power series looking locally at those points. So let's look at a typical application of Rouche's theorem. So we can show that the polynomial shown here, 3z cubed minus 2z squared plus 2iz minus 8, that those zeros lie in a particular annulus. So you can say that they lie outside the unit disk, so further than a distance of 1 from the origin, but they must all lie within a distance of 2 from the origin. So they have to be in this annulus at a distance between 1 and 2 from the origin. So the basic idea of how to use Rouche's theorem here to show that there's no zeros inside the unit circle is to compare your polynomial to a non-zero constant. So a non-zero constant function has no zeros. So we can successfully compare our function to that function with no zeros using Rouche's theorem. Then we should be able to conclude that our function itself has no zeros. So what we're going to do is, so first of all, so when norm z equals 1, so we're on the unit circle, what we'll do is compare our p of z to the constant term of our function, which is negative 8. So if we look at the difference between p of z and negative 8, that's equal to the norm of 3z cubed minus 2z squared plus 2I times z, right? And, well, using the triangle inequality, that's less than or equal to 3 times norm z cubed, so that's just 1, plus 2 times norm z squared, so that's just 2, and then norm of 2i is 2 times norm of z is 1, so that's another plus 2, and that is equal to 7. And indeed, that is less than the norm of negative 8, right? So if we take, so negative 8 here, that's our f of z, p of z, this is our g of z. So the norm of f of z is minus So the norm of f of z minus g of z is less than the norm of f of z on the unit circle, right? So that means that inside the unit circle, they must have the same number of zeros. So Rouche's theorem implies that p of z and -8 have the same number of zeros in the unit disk. So that's and nice shorthand. So in the disk around 0 of radius 1. So oftentimes that's denoted by capital delta. Okay, so we have no zeros in there. Now, on the other hand, if we look at, so when the norm of z equals 2, so the basic intuition here is that we know that our polynomial is a degree 3 polynomial, so it should have 3 zeros, right? And so we want to compare that with a function which obviously has 3 zeros. And so a function which obviously has 3 zeros is this leading term of the polynomial, right? So that's equal to 0 3 times at 0, right? It has a multiplicity, a 0 of multiplicity 3 at 0. And so what we're going to do is compare p of z to 3z cubed, right? And by the same type of using the triangle inequality, what we find is we have 2 times norm z squared plus 2 times norm z plus 8. Right, just using the triangle inequality and then substituting in 2 there, what we find is 8 plus 4 is 12 plus 8 is 20. And so that's equal to 20. And the norm of 3z cubed, right? So the norm of 3z cubed when the norm of z equals 2 is equal to 3 times 8, which is 24, right? So that equals 24, and 20 is less than 24, right? So if we take this to be our f of z, this is g of z, right? That tells us that f and g must have the same number of zeros in the disk. Oh, right. So sorry, back in the first part, which is 0. So the same number of zeros in the disk, which is 0. And then down here, so Rouche's theorem implies that p of z and 3z cubed have the same number of zeros in the disk around 0 of radius 2, delta sub 2, which is 3. Okay, so our p of z has 3 zeros in the disk of radius 2, but it has no zeros in the disk of radius 1. So this implies that p of z has 3 zeros. So this is counting multiplicity. You could have double zeros, counting multiplicity in the annulus around 0 of inner radius 1 outer radius 2. Okay, so that's the basic idea. So with a polynomial, that's pretty much the idea. You can sort of put a bound on a lower bound on how far your zeros are away by comparing to the constant term, and an upper bound by comparing to the leading term with the degree of the polynomial. And one more thing I want to point out about Rouche's theorem is that, in fact, you can change this minus to a plus if you want. Right. So, in fact, this works for plus and minus. So we gave the proof for minus, but the conclusion is that f and g. So basically, for the plus version, you can look at f of z plus g of z as the same thing as f of z minus negative g of z. Right. So if you have this hypothesis for plus g of z, that's the same hypothesis for negative g of z, right? So you would conclude that f of z and negative g of z have the same number of zeros, but the number of zeros for negative g of z is the same as the number of zeros for g of z. So Rouche's theorem works whether you have a plus or a minus there. So I thought it might be helpful to provide you with an alternate form of, or formulation of Rouche's theorem. So here's an alternate formulation. Suppose you have two analytic functions on a domain containing a typical curve gamma and its inside omega. If h of z's norm is less than f of z's norm on that curve, then f and f plus or minus h, and then the plus or minus of that, any one of those four possible functions there, they all have the same number of zeros in omega, counting multiplicity. Okay, so the proof is simple. It's just using the version of Rouche's theorem we already established. So note defining g of z to be f of z minus h of z, then f of z minus g of z equals h of z. Right, so we have just substituting into the inequality, f of z minus g of z, that norm is less than the norm of f of z. Right, so thus g, which is equal to f minus h, so f of z minus h of z, has the same number of zeros as f. So now to get the other ones, so just note that if we change h of z to negative h of z, this doesn't change the hypothesis, so it doesn't change the inequality. This doesn't affect the inequality. The given inequality and changes g of z to f of z plus h of z. Right, g of z to f of z plus h of z. So the conclusion holds for f of z plus h of z, and of course this g of z, that g of z has the same number of zeros as negative g of z. Right, so now just note g and negative g have the same number of zeros. To get the conclusion, for negative f plus or minus h. So basically, if you have some function f, and on a curve it's bigger than some other function h, then you can consider, you can add h or subtract h from f, or add or subtract f from h, and that resulting function has the same number of zeros as f inside the curve. It might be helpful to keep the man with a dog on a leash metaphor in mind here. So like the original version of Rouche's theorem is f minus g less than f, right? So basically in this case, this is like distance between the man and the dog. So this is the man and this is the dog, and this length of f, this is the distance from the man to the tree. So in this case, if the distance between the man and the dog is less than the distance from the man to the tree, then you can conclude that the man and the dog could walk around the tree the same number of times. In this version, you have h is less than the distance from the man to the tree. So this h here is like the length of the leash. So this is the leash here. So that h being the leash, you would have f plus h equals g, right? So man plus leash, that leads to the dog. So if the length of the leash is less than the distance to the tree, the distance between the man and the dog is going to be less than the distance to the tree. So that sort of tells you why this implies that. And if the distance from the man to the dog is less than the distance to the tree, then the distance from the man to the dog is just the length of the leash. So that tells you why that one would be equivalent there. So it's just sort of two different ways of thinking about it. You're either thinking about the distance from the man to the dog in this one, or you're thinking about just the length of the leash. They both have sort of a nice intuitive flavor to them. So let's illustrate with this example. The number of solutions to this rational equation in the unit disk. So what we'll do is so the given equation is equivalent to z squared minus 4 times z squared plus 6 plus z squared plus 4 times 2z squared minus 1. That is equal to 0. So what we want to know about is the dog. So this is our full thing. This is the dog. And what we can do is we can split it into two pieces here. One is going to be man and one is going to be leash. And this could take a little bit of trial and error to figure out which one is the best to choose. But in this case, this is going to be the man and this is going to be the leash. So this will be our g of z. This would be our f of z. This would be our h of z. So writing it out, f of z equals, it's negative 24 plus 2z squared plus z to the fourth, and h of z is equal to 2z to the fourth plus 7z squared minus 4. And so basically, heuristically, this f, so you have the 24, the z is going to be on the unit circle, so take z to be on the unit circle, which is the boundary of that disk. We have this 24 and then plus 2 times something on the unit circle plus something else on the unit circle. So basically we would expect roughly that this is like negative 24 plus something whose norm isn't worse than 3. So that would be roughly of like norm 21, and then this one down here for h of z we have a negative 4, and then we have like a 7 and a 2. So roughly speaking, that couldn't be worse than like 13. So this one is going to be roughly have norm be 13, and this one roughly is going to be 21. So that's how you could decide, so this one should be the man, right? This should be the man further away holding a leash of length 13, and then the dog won't be able to wrap itself around the tree. Okay, so that's how you could figure out which one is man and leash. And to make this more precise, we can say that norm of f of z, that's the same thing as, so we want to estimate this from below. We want to say that f is bigger than h in norm. So this is the norm of 24 minus 2z squared minus z to the fourth, which is 24 minus 2z squared minus plus z to the fourth, and this is bigger than or equal to, by the reverse triangle inequality, 24 minus the norm of 2z squared plus z to the fourth, right? Because we know this norm that norm can't be bigger than 3 by the triangle inequality, right? So that's definitely the smaller one, and so because of that, right? So this thing here is less than or equal to 3, so that difference is greater than or equal to 21, and just as we predicted, just by our rough calculations, and then just straightforwardly by the triangle inequality, this is less than or equal to 2 plus 7 plus 4, which is 13. Right? And that is less than 21. So we see that h of z is less than f of z, and so then that implies that f of z plus h of z that has the same number of zeros as f of z. Right? So g of z and f of z have the same number of zeros in the unit disk. But you see, so the thing is that it's easy to compute the number of zeros of f of z in the unit disk because f of z is factored, right? So, but f of z, that's equal to z squared minus 4 times z squared plus 6 equal to 0 only has solutions outside the unit disk, right? The solutions are 2 and negative 2 and root 6i, negative root 6i, and those are outside the unit disk. So G has no solutions in the unit disk, and so neither does our original equation. So now we're going to start talking about so basically how an analytic function maps the plane to itself. So it turns out that Rouche's theorem is very useful to get us started here, though it's not obvious at first glance. So we'll just sort of take this up as an independent line of investigation, just natural question to ask. So what we can ask basically is, if we have an analytic function defined on a domain D in the complex plane and we apply an analytic function to it, and so like what does the image look like over here? And I mean, the most basic question you could ask, so question is f of d itself a domain? So that is is it connected and open? Well, it's not hard to believe that that the image of D here is going to be connected in the sense that any 2 points are connected by a path. Because if you have points connected by a path over here, then you just apply f to that, right? So that's gamma. Then you're going to have another path, which is just f of gamma over here. Right? So this will be f composed with gamma. And so this is p and q, then you'll have f of p and f of q being connected by that just composition curve there. And so that's not so difficult to believe, so I won't concentrate on that anymore. The question about being open is more interesting and subtle. So you could imagine, for instance, something like this. Like you might imagine that something your f could possibly do is like take your domain, let's imagine just like cutting the domain in half like this, and you can imagine what f might do is like fold the domain over itself, and so it might do something like, like the 1/2 gets mapped over one half gets mapped over here like this, and then it sort of gets folded so that the other half ends up like that, right? And so your image looks something like this in total, right? And then now you have some kind of boundary points. Right? So you have points in the image here, which are along this boundary where when you put an open set around them, it intersects the complement of the image, right? So for every other point here, if you take a point like in this picture that I've drawn, you can always draw a little circle around it, such that all of those points are in the image in this picture. So you have to remember that the black lines, because F is a domain, or because D is a domain, those thick black lines actually are not included in the set D. And so these thick black lines in the right are not either. So those points don't count. Yeah, so you might wonder whether an analytic function can do something like that. And the answer is that it can't do something like that. So the answer to our question here, whether f of d is a domain, is yes. So it turns out that the image of a domain by an analytic function is an open set. So that is, whenever you have a point w naught, say, in the image of f, then you have to be able to draw a little circle, right, at least of some radius, such that all of those points in there are in the image of your function. Okay, so if w naught is being hit by z naught over here, then there's going to be some points nearby z naught that are getting mapped onto that little disk around w naught. And the way to see that is pretty remarkable. So suppose that f of z is analytic and non-constant on a domain D. Z naught is in D, and f of z naught equals w naught. What we'll do is just expand f in a power series around z naught. So f of z then is equal to, first term of the power series is f of z naught, so that's just w naught, and then plus then the other terms of the power series. So we have a1 times z minus z naught plus ... right? And we'll just, so like if a1 were to happen to be 0, we could discard that one, right? And we'll just discard all of the terms that are 0 until we hit one that is not 0, right? So am times z minus z naught to the m plus ... right? Where am here is not equal to 0. So in other words, w naught here, and so we have equivalently f of z minus w naught, this function has a 0 of order m at z naught. Right, so it has to have some order because we know that our function is not constantly equal to 0. Right, so f of z is not the constant w naught, so f of z minus w naught can't be the constant 0. So we have to have some m where this is true. And so what we have here is if we pull the z minus z naught to the m out, we have that times am plus blah, 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 right? Okay, so going along with our intuition up in this picture, basically this picture up here, what we want to do is look sufficiently close to z naught. So sufficiently close to z naught, so basically our power series here, what it tells us is that, if we come close to z naught, this will be just close to the constant am. So this is roughly am when z is close to z naught. Right, so this tells us that close to z naught, f of z minus w naught is approximately just the polynomial am times z minus z naught to the m. So heuristically, by centering at z naught and w naught in the domain and range, f has the same same local properties as a constant times z to the m. And so constant times z to the m, if you think about what that does as c times z to the m around 0. So if you think about what that looks like, and so if there's 0, your constant times z to the m. Let's even just ignore the constant, do this as a composition. Z to the m is just, it's stretching, so when z is small, it's going to be like contracting things in, right? And it's also multiplying the angle by m. And so what happens is that every mth of this circle, so it takes this circle on the left and divides it into m congruent pieces, right, etc. And each of those pieces ends up, the angle here, this is 2 pi over m, that gets multiplied by m, and so that wedge there gets mapped onto the entire circle, right? So that gets mapped on, so this edge here goes there, and that whole wedge gets wrapped around until this edge here ends up on the same, ending up on the same segment on the other side when it gets pulled around. Right, so this is m to 1 here, right? At least away from 0. So 0 kind of goes to 0 m times, and every other point in here gets hit m times, one time for each wedge on the left there, and then the multiplication by c. So then multiplying by c, that sort of just rotates and scales this picture, right? So roughly speaking, this is going to get rotated because multiplication by constant complex number is just a rotation and a scaling, right? So that's basically and so that doesn't really change very much. So again, our function is going to be m to 1 as long as you interpret m to 1 at 0 as meaning sort of by multiplicity. So in particular here, we have, so in this picture we have 0 going to 0 by this mapping, but also any point near 0, right? So 0 over here, any point sufficiently near 0 is getting hit, and in particular it's getting hit m times by something in the domain. So basically what we expect here, so by analogy from, so f of z equals w naught plus am times z minus z naught to the m. So if, so w naught here is f of z naught. What we expect is that if this function sort of acting like one of these polynomial functions near z naught, then it should look sufficiently like this picture up here. So we should have, for every w which is sufficiently close to w naught, so what we expect from this is that for all w sufficiently close to w naught, w is in the image, so is in the image of f, and in fact f is m to 1 for all z close to but not equal to z naught. So here's a precise statement we can make of all of this. So suppose f is analytic and non-constant on a domain. We have a point in the domain and then the image of that point. So if we take a w sufficiently close to that image point, then the number of solutions to f of z equals w is the same as the number of solutions to f of z equals w naught. And so our proof here is, we'll first consider z so close to z naught that z naught is the only solution to f of z naught equals w naught. So since f of z minus w naught has isolated zeros, right, any analytic function's zeros are isolated, we can take z close enough to z naught that z naught is the only solution to f of z equals w naught with multiplicity m, say. Now we know how to count solutions of equations, to compare the number of solutions of an equation to the number of solutions to another. So considering this and that, so we can consider the difference. Right, we're going to use Rouche's theorem. Consider the difference f of z minus w naught minus f of z minus w. Right, that is the norm of w minus w naught. So what we want is that this is less than f of z minus w naught, right, in norm, because we know the number of solutions to this for our z sufficiently close to z naught, right? So we can just take like a little circle, a small circle around z naught. So we know the number of solutions inside that small circle. So what we want is that, so we want this, and we want that on the boundary of a small disk around z naught of radius r. Right, so we're considering, we have our z naught and we have a small disk of radius r here, where z naught is the only solution to f of z equals w naught with multiplicity m in there. And so, well, and so we just have to choose w close enough to w naught in order to make this the case. But norm f of z minus w naught has a minimum on the boundary of the disk of radius r around z naught, right? Say delta. And so this is a theorem in analysis so on a closed and bounded set, this continuous function has to have a minimum. So we just need to choose, w within a distance of delta of w naught for this to be the case. And then by Rouche's theorem, then f of z minus w has m solutions in the disk around z naught of radius r. Okay, so we'll work more in this direction in the next lecture, so we'll say more, but for now what we know is that at least our function near an image point has to look like this picture up here. It looks sufficiently like a polynomial, so in particular any nearby point is going to be hit, and so what that's going to imply is that the image of our domain under our analytic function must be open. So we'll explore more of that next time.